Experiment 9 is about electrophilic aromatic substitution, application of green chemistry in high-performance liquid chromatography or HPLC. Objectives of the experiment are to perform green bromination reaction on a substituted benzene ring and to identify and determine purity of products by IR and HPLC. Mechanism of electrophilic aromatic substitution. The reaction is a substitution on the aromatic benzene ring with an electrophile. The benzene is acting as the nucleophile. In the experiment, we are doing green bromination reaction, and the mechanism of substitution is the same as above in the conventional bromination. In the experiment, we are combining cerium plus 4 and Br minus from KBr, forming Br plus, which is the electrophile, and then cerium plus 2. Cerium plus 4 is reduced to cerium plus 2, and then Br minus is oxidized to Br plus. Potassium bromide and steric ammonium nitrate have less hazard than the fuming liquid Br2, typically used in conventional bromination. Fuming liquid Br2 is actually a poison. FeBr3 or iron 3 bromide is acting as a catalyst and as a Lewis acid. It reacts with the fuming liquid Br2, forming Br plus and then FeBr4 minus. This Br plus, which acts as the electrophile, is the same as the electrophile below, formed from the green bromination reaction. In the experiment, there's another reactant, which is the aromatic benzene ring structure acetanilide with an amide as a substituent. This amide substituent is electron donating, activating the para position in the structure as well as the ortho positions in the benzene. There is one para position and there are two ortho positions in the ring. This carbon will react with the Br plus, and this ring is nucleophilic and the Br plus is electrophilic. So this carbon forms a bond with the Br plus, and then there's an H and this carbon. So take note that the benzene ring in the structure has 5 H's. One here, second H, and then third, and then another H in here, another H in here. There are 5 H's. That's why there's an H in this carbon. So when this carbon makes a bond to the Br plus, it's utilizing this double bond, and this carbon now is depleted of a bond. That's why it's a plus. It creates intermediate structures. Then 3 other resonance structures can be drawn, which are intermediate in the mechanism. So these are called resonance stabilized intermediates. So starting from this carbocation, this double bond can shift to this side of the ring, and then this plus now is going to be in this carbon. Another shift of the double bond makes a double bond in here, and then the plus goes in this carbon. But because the nitrogen has lone pair, it's gonna donate that lone pair into the ring all the way to the plus. So you have 2 arrows making a double bond from end to the carbon, and then this double bond will shift towards the plus, forming a double bond in here, assigning a plus on the end. So you now have 4 resonance stabilized intermediates. When the Br is picked up by the carbon, the aromaticity of the benzene ring is destroyed, temporarily destroyed. However, at the end, that aromaticity is retained. So the final step in the mechanism is when this H is kicked out, and then forming a double bond in here, in this side of the ring, and then another double bond in here, while one bond from carbon to N goes to become the lone pair. The Br now is left behind. So you now have what is called a para-substituted benzene ring. So it's called para-brominated acetanilide. When the H is kicked out at the final step, it's picked up by the FeBr4 minus, forming HBr, and then FeBr3, which is the original catalyst, and regenerated back in the last step. There is another product that is formed when this carbon attacks the electrophile. So again, there are 5 H's. This carbon can pick up the Br+, forming a bond from this carbon to the Br, and there's an H. So there's a carbocation formed because in this original structure, the bond is now shifting to form a bond to the Br. Therefore, a plus is formed in this carbon. Now you can write 3 more structures, 3 more resonance stabilized intermediates coming from this structure here, which is the carbocation. When this double bond shifts to this side of the ring, this plus goes to this carbon, now this one. Then another shift of the double bond, forming a double bond in this side, will now put a plus in this carbon. So there's going to be 3 carbocations in the ring, 1 here, and then 1 here, carbocation, and then another carbocation in here. So the last intermediate would now be the same as above when the N lone pair goes to form a double bond, and then the double bond shifts all the way to the plus. So when this becomes a double bond, this double bond shifts, otherwise this carbon becomes 5 bonds. And then shift the double bond in here, again shifting the other double bond. So you're shifting the double bonds all the way to the plus. So from the lone pair all the way to the bottom. Then it assigns a plus on the N. The last step, the same as above, when the H is kicked out in here. So the H now is kicked out, forms a double bond in here, and this one bond forms a lone pair on the N. Therefore, the plus disappears. This H plus is now picked up by the FeBr4, forming HBr, and then FeBr3 left behind, forming back the catalyst, the original catalyst. So now the Br goes to the ortho position. It's now called ortho-brominated acetanilide. So in the experiment, we want to know if we actually form 2 products or just 1 product. The ortho position is more sterically hindered than the para position. So we will see from the data if we actually form 2 products or just 1 product. So I have here already the reagents and then the starting compound that we're going to be using. Starting compound is acetanilide, and then the reagents are ceric ammonium nitrate and then potassium bromide. So we're doing day 1 of the experiment, and then I'm doing, again, the reaction is called bromination reaction. So the procedure is in the next page, and then I already have everything in here. So I have the E-flask, 50 ml E-flask, and then I have the starting compound, starting reactant, acetanilide, it's white powder, and then I have also the 95% ethanol, and then I'm gonna put it in the E-flask, these 2 together, and then I'm also going to weigh potassium bromide, it's KBr, and then ceric ammonium nitrate, and then put it in the beaker and then dissolve that in water. I'm gonna stir it at room temperature for 10 minutes until white crystals form, and then chill it in ice water. We are now going to weigh the starting reactant, which is acid nonylide. Okay, so I already have inside the balance the weighing boat, so I zeroed it. So I'm going to now weigh 0.25 grams. Okay. Okay, the weight right now is 0.253 grams. So write that down, please. It doesn't have to be exactly 0.25 as long as we know the weight that we're starting out with. So again, the weight is 0.253 grams. So the reactant that I weighed, I'm now going to put it here in the e-flask. So I put everything, and then I'm going to now add 95% ethanol in here, 4 ml. So 4 mils. So again, I typically pipe it up and down first, and then this is calibrated to 1 ml. Okay, so I'm gonna put 4. Two. So 2, 3. 4. So then I cap it, and then I'm gonna stir it here. So I'm going to put a stir bar. So a stir bar. So I have a little tiny stir bar over here, magnetic stir bar. And then I'm gonna put it here, and then I'm gonna stir it. So this is now the weight of the KBR. So KBR is potassium bromide, 0.25 grams. So KBR, okay. So KBR is white. Okay, looks like that. So I have inside, in the boat, it's KBR, 0.25 grams. So write that down, please. The other reagent is an oxidizer, and that's ferric ammonium nitrate. And I already weighed 1.500 grams. And then it's in the balance, and it's colored orange. So if you can see, as you can see, it's orange. So bright orange, like color of carrots. Okay, so that's your other reactant. So I will now mix together the KBR and the ferric ammonium nitrate in this beaker. So just gonna mix it up. And then also this oxidizer. And then I'm gonna dissolve this 2 reactants or reagents in 4 ml water. So it's just RO water. So 1, 2, 3, 4. So I'm just gonna mix it up, stir it. So this should be soluble in water. Okay, and then I'm going to add it into the solution. It's already in here, so dissolve. So that's in ethanol. Okay, so it's dissolved fast. So I'm gonna add it dropwise into this solution. So using a plastic pipette, I'm gonna add it here. So because it's water, actually I don't have to pipe it up and down because it's heavy, so it doesn't really drip. So it's not volatile. So water, aqueous, is not volatile like other organic solvents. So I'm just gonna add it here. So I go close. So I'm gonna add it dropwise, and I will stir it for 10 minutes. So 10 minutes, we're gonna stir it. And we should form the, so it actually is changing color right now. So that's a good sign. So now I can see some precipitation. So we're gonna do it for 10 minutes. After 10 minutes of stirring, it looks like this. The sample. Okay, and then I'm gonna turn off the stir plate. And then I'm now going to chill it here in ice water bath for maybe 5 minutes. Okay, until it's cold to the touch, and then we are going to do vacuum filtration. We are going to do vacuum filtration. So this is the filter paper inside the balance. So I weighed it at 0.208. So again, write this down. The weight of the filter paper is 0.208 grams. We're now doing a vacuum filtration, so I will have this going. So now I'm going to filter this. So we want the solid to be in the filter paper. Okay, so I'm just gonna pour it, and then at the same time rinsing it out with RO water. And then try to transfer as much as possible so that we get the optimum amount of the product that we got. So rinsing it out in circular motion around the e-flask, and then swirl it a little bit to transfer everything. So now this is now the filtrate. So it looks like I don't have anything that went through, or I don't have any solid that went through. And this is our product in here. Okay, so it's white. It's and the color is uniform. So we're gonna let this dry for a week, and then the next lab period, and then we are going to weigh. It should be dry by then. And now I'm gonna unhook it from the water aspirator. So typically I press this tubing. If I turn it off immediately, there's gonna be a back pressure, and that water is gonna flow back in here. So you typically just press this and hook it, and then I have that off. So it's done. Okay, and then basically this is my filtrate. So it goes to the waste. Okay, and then this is now our sample, and then we're gonna pick out that stir bar later on, so it still looks wet. Okay, and then this is basically our filtrate. So that's our filtrate. Okay, so it's clear. This is the sample a week after drying, so it should be dry. So it's white, powdery, and now we are going to weigh the sample. So again, we had the weight of the filter paper, and then I'm gonna transfer this into a weighing boat. So I zeroed the weighing boat. take it out. So open the sliding door, and then I'm going to close the sliding door, and then I'm going to take out the sample slowly. So it's flaky. Sample is flaky. So now, since I zeroed that the weight of the boat, the weighing boat, this is basically just the weight of our filter paper and then the sample. So now this is the final weight of our sample plus filter paper, 0.393 grams. So write this down in your notebook, please. 0.393 grams. You are going to subtract the weight of the filter paper. That gives you the weight of the sample obtained from the bromination reaction. So after we weighed the sample, this is now the sample in the weighing boat, the filter paper and the sample. To correctly preserve the integrity of my sample, what we can do is to put it in a vial. It's covered. Say for example, so remember, we converted the starting compound acetanilide to a brominated acetanilide. So we actually synthesized something new from here to here. So this is now a completely different molecule from the starting compound. So now the next step is we are going to analyze this sample. But because I want to preserve the integrity of my sample, I don't want it uncovered. So one way is I want to put in the vial. So I have a vial. I took the tare weight of the vial, which is 13.361 grams. And I will also put a label. So I created a label, which is this label here. So the label is, this is just a tape. So experiment 9, brominated acetanilide, and then the date that I'm doing the experiment and the tare weight of my vial, which is 13.361 grams. So I should put grams just to make it complete. So that's grams. Okay, so that's the tare weight of my vial. Because I might use it later, so one way is I want to get the weight of the vial, and when I go back to this sample, I want to know that it's actually still the same weight. Or if I want to go forward, move ahead, or do something else more, then I know the amount of the sample that I put in the vial. And it's going to be a screw cap vial. This is the cover, this is the lid. So I just push the filter paper with the sample into a weighing paper, and I want to scrape the sample to the weighing paper so that I can transfer it into my vial. So it's very flaky, and I have a couple of weighing paper here. It's like wax paper. The sample will not stick to the wax paper, so the sample actually lifts off quite easily from the filter paper. But because I want to make sure that I don't spill it all over the place, then I want like multiple weighing papers so I can collect as much as possible in case I accidentally spill it. Okay, so I'm just gonna put it back in here, and now I can put this sample, it's very flaky, it's powdery flaky, into my vial. Okay. So I transferred everything, put it back, and that's going to be the weight of the sample that I will store, and that's the weight that I will put. So the weight of the sample plus the weight of the vial is 13.532 grams. So now I will subtract 13.532 minus the tare weight, or minus the weight of the vial, which is 13 0.361 equals, that's going to be the weight of my sample, 0.171 grams, 0.171 grams. So that's my label. Okay, so it's preserved because now I don't have the air oxidizing my sample, so I can store this longer time than if I just have it in here. However, for our purposes, because we are not really doing more than this sample, I did not put this in the procedure, but this is a technique to preserve your sample just in case you have a multi-step reaction, meaning that you are going to do more reaction on this synthesized product. So this is now our sample. Again, I label it with the date, and then tare weight of my vial, and then the weight of the sample inside the vial. Part B is about IR spectroscopy. So we are analyzing the solid sample, the brominated solid sample that we synthesized. And this is now, again, the IR spectrophotometer from Thermo Scientific Nicolay IS-10 IR spectrophotometer. So first thing to do is, again, this is the software associated with the IR, and the software or the application is Omnic, and then I'm going to click on it, double click, and then this will show up, and then I just do OK, and I'm gonna do full view, and now I'm going to scan the background. So one click and then just do OK, and then again it scans the background, which is just the air. So you will see this fill up, and then when it scans 8, it will stop. Then it's scanning the background, and I would just do add to window 1. No, I basically just scan the background, and then I can subtract this from the spectrum, and then what we get is, so the computer subtracts it from the sample, and what you get is the final spectrum of your sample without the background. So now I do no. So now it's clean, it's clear, and then we're ready to run the sample. We are now doing the IR of the sample. So this is the vial where I have the sample. So brominated anilide sample. So I will now put a little bit of the sample into the sample holder. So use a spatula, and then I'm gonna put just a tiny amount of the sample into that hole. And then again, the ATR pressure tower, I'm gonna press that sample onto the plate. You hear that click, and then we are now going to click on the collect sample icon. So my mouse is hovering on it, so I will click on it and then click, and then another click, and then I will now be watching this part here to fill up with blank. So now when it's filled up, I scanned 8. So I will do add to window, yes, and then I now have my sample. This is now the whole sample of the brominated product that we got from the experiment. So I will now label. So you press find peaks. So find peaks, if you hover the mouse, it will also tell you what it is. So find peaks, and then I will put the cursor way up here. So that's basically the threshold, and I will click replace, and I will also click on full scale, so I can see everything even at the bottom over here. So I will click full scale, and then I have all the labels. This is now the IR spectrum of the brominated sample, and I labeled everything. You will get a data, you will get this printout, and you are going to compare this with the next sample that I'm going to run. So take note of this region, take note of this region, take note of that region, and this region around here. So this would be the absorption bands that I labeled absorption bands, absorption bands. So this is now the IR spectrum, percent transmittance versus wave numbers. So again, it's a plot of percent transmittance versus wave numbers. It's going from low value to high, 45 to 100, and this would be 4,000 to 500. So the next step is to clean the plate. So the same thing as if you have a liquid, the same idea. You're gonna get cotton, so get a little bit, and then you damp it with isopropanol. Okay, so you clean it with the isopropanol, and then so this is the protocol, and then you are going to raise the ATR pressure tower, push it away from you, and then you are going to wipe it out, and then also the tip of this tower, pressure tower. So, and then do again to make sure that it's clean, so that for the next user, or if ever you have another sample. Okay, and then the tip. So you have to let it dry for about 5 minutes. So it should dry fast, but to make sure that there's no isopropanol contaminating your next sample, you have to leave it longer. Okay, so at least 5 minutes to aerate it. We have a second sample, which is the starting compound. This is starting reactant, which is the acetonilide. So I want to run an IR spectrum of the original sample, so we can compare the brominated one versus the starting compound, which doesn't have a bromine. So the same protocol, you're going to put a little bit of the sample. So use a little spatula, and then just a tiny bit of sample into that hole. And then okay, and then we're gonna collect sample icon. We click on it. So we click again on that icon, collect sample, and then okay, okay, and then the same thing. You are going to look at this bars here that it's scanning. Okay, we're doing 8 scans. So add to window 1, yes, and then so 1 is to label the peaks, find, either you do find peaks again. Okay, I think that's it, and then we are now going to print. So the same thing, you can either print over here. So you are now going to compare the IR spectrum. This is before bromination and then after bromination. Is there a significant difference between the two? So you will have this data available for you. IR spectra of disubstituted benzenes. In this slide, there are 3 IR spectra. First is the para-substituted benzene, or the one for substitution in the aromatic ring of the benzene. Second is the meta-substituted benzene, or the 1,3 substitution. Third is the ortho-substituted benzene, or the 1,2 substitution. These 3 are structural isomers or constitutional isomers. There is a subtle difference in the IR spectra of the 3 examples in the region of 2000 to 1700 per centimeter, also referred to as the overtones for disubstituted benzenes. For the para, you will have 2 bands, weak absorption bands in this region, 1, 2. For the meta, you will have 3 bands, weak absorption bands in this region, 1, 2, 3. For the ortho, you will have multiple bands, weak absorption bands again in this region. So para, isomer, 2 absorption bands, meta, isomer, 3 absorption bands. For the ortho isomer, multiple absorption bands, they're all weak absorption bands. So in the experiment, we brominated acetanilide. So we have para, or ortho, or meta. So from the IR, we will determine, did we just get solely para, or plus ortho, or meta for the brominated product obtained from the experiment. This is now our samples for HPLCs. I'm going to prepare the samples in a vial, HPLC vial. So we have 2 samples, the starting compound, the acetanilide, the starting reactant, and then I already weighed 2 milligrams of the starting acetanilide over here. So it's actually crystalline. And then I also have the other sample, which is the synthesized product, the brominated acetanilide. So we have a brominated acetanilide synthesized product, and I already weighed 2 milligrams, so it's fluffy, while the starting compound is actually crystalline. They're both 2 milligrams. So now I'm going to dissolve each one using acetonitrile HPLC grade. Okay, acetonitrile is the solvent, and I'm just going to put in 1 ml each. So using the calibrated pipette, so 1 ml HPLC grade solvent, and then the other sample, the same thing. So our starting compound is basically our reference, and we want to compare the product. Okay. Okay, so these are our samples, and I'm going to vortex these 2 samples. So I'm just going to mix it up, vortex it. Okay, so just want to make sure that they're dissolved so I don't see any particles at the bottom. So I'm going to filter into the HPLC vial. So this is the filter. It's 0.45 micron PTFE filter. So to make sure that there are no particles undissolved that goes into the HPLC column. So I will use a syringe. This one, it's plastic, it's disposable. And then I will withdraw about a ml. Okay, so that's about a ml. And then I will put it over here. And then I will filter it through the HPLC vial. So I will cap it using this cap. So that was our original reactant acetanilide. So I want to mark it to make sure that I don't confuse it with the other ones. I mark it as A. Okay, that's the sample. So I will put it aside just in case I need to refilter again. So now we have another sample, which is the brominated one. Okay, I'm gonna filter it again. So again, the syringe, and I will withdraw 1 ml because remember I actually dissolve it in a ml. So I will withdraw again the entire sample and then into the filter and then push it into that vial. So now I will get another cap. So cap it. So this is the other sample. Okay, so I will now put it in the HPLC carousel. This is the plate where you put the samples. I'm just gonna turn it. So I think I will use this slot in here. So I will use this A1 and then A2. So I will put the first one on A, labeled A on A1, and then A2 is the brominated one. So this is the HPLC instrument. This is called the Ultimate 3000 Thermoscientific Dionics. So this is the pump. So there's a pump in here. So you can hear the clicking sound. So what it's doing is it's mixing the solvent on top. So we have a mobile phase on top composed of 3 different kinds of solvents. So the instrument software can actually mix 2 combinations or 3 combinations or just single solvent, and then can also do what is called a gradient. You're increasing the concentration or the amount of each of the solvent mixture. So this is the mixing system, or the pump mixes combinations up to 3 different solvents. So those are the mobile phases. So for every chromatography, you have 2 things: the stationary phase and then the mobile phase. In this case, you have the mobile phases on top. It's going to be pumped into the column. So the column is down here. So this is where the separation happens. So the column contains the stationary phase where the separation will happen. So it's actually under pressure. So it has very tiny particles inside and can really separate components that are very close in polarity. So that is the strength of this instrument. And also, it's automated. You don't have to do the injection. There's an injector port, and then there's also the detector. So the detector, you have a UV and as well as visible detector. So we are going to have, you can have different wavelengths that the sample can absorb. So you can set it on that wavelength and it will detect on that particular wavelength. And then we have what is called the fraction collector. So the fraction collector, after it separates into the column, it's going to go out in this tube, a Teflon tubing, and then it will collect into each of these tubes in here. So you can program the instrument so that you are collecting each fraction. So similar to the column chromatography that we did, ferrocene, acetylferrocene, this one you can program it so that you are not manually collecting it yourself. The instrument collects for you different fractions, and you can program it at a certain time and certain peak that is coming out from the column. So again, the separation is happening from the column, and then it goes out in this tube, and then you can collect. If you are not going to collect, it will just actually goes to the waste. So the waste is gonna be collecting in here. Okay, this is the waste. So if you are putting in a solvent, something has to come out. So now the instrument is actually controlled by a software. So the software is called a Chromeleon 7. So right now I'm pumping it to 1 ml per minute. And the pressure is 73 bar right now. And the combination of solvent is, this is water, 50%, and then 50% acetonitrile. So on top, in here that I've shown you earlier, this is water, okay? The first container, the first bottle is water, and then, so this is labeled as A, B, C. So that's A. And then B is methanol, A is water, B is methanol, this is acetonitrile. So notice that the mobile phases are actually polar, like water, methanol, acetonitrile. This is reverse phase HPLC. The stationary phase, which is the column, is actually non-polar. So the mobile phase is polar. So when we did the column chromatography, ferrocene and acetylferrocene, the adsorbent or the stationary phase is actually polar. So that's normal phase. And then the solvent that we use in that experiment is petroleum ether, and then combination of petroleum ether and ether. So the mobile phases in that experiment, mobile phases are actually non-polar. So it's opposite polarity. If you're doing reverse phase, that means that your stationary phase is going to be non-polar while the mobile phases are going to be polar. So I am now going to make an injection. I put the vial on a green slot and then A1. So I'm gonna click here to add a new injection. So I'm going to put A1, GA1 on it. And then the other one is going to be GA2. So the first one is standard, and then the next one is going to be, so I'm going to rename that as brominated product. Okay, so save. So I'm now ready to make an injection, and actually you can see real time here. So when I make an injection, it's gonna start here. So this is basically by minute. So it's by minute over here. It's minute. And then at zero, it's gonna inject, and then once I inject the sample, you're gonna see peaks. Okay? So in here, you also have the detector, UV, and then visible. Okay? So UV 272 nanometer, and then another wavelength 667 nanometer, that's visible. Okay, so now I'm ready to make an injection. I go back in here, so I do resume over here, and then I can now make an injection. So this is our sample in here in the carousel. So in the plate, so it's 8 by 5 slots that you can run. So there's actually 3 5 by 8 slots. You can run a lot of samples in here. So when I make an injection, it's now getting ready. So it's now going to inject. So it's now injecting the sample. Okay, so that's the injector port. And then it's actually going to inject 10 microliters of the sample, and we are on slot GA1. And this is the flow rate, 1 ml per minute, and the pressure is 61 bar. So it's now going to inject. The sample is currently injecting. So it's gonna go into the column. So it's automated. So now it's gonna inject. This is the syringe. It's injecting. The instrument does its injection, and it's gonna go to the column. So now it's coming up. It's done, and then now it's going to run. So it injected, and then we're gonna watch if the peak comes out. This is now the sample, standard acetonilide. As you can see, there's only a 1 peak, and the baseline is clean. So it's gonna stop at 3 minutes. So this sample came out at about 1.5. It's about 1.58 minutes. So now it's injecting the second sample on that second slot. So that's the brominated product. So again, it's going to inject into the column. So now it's going to inject through here. And then it's going to go to the column. This is now the real-time HPLC chromatogram of the brominated product, and as you can see at 1.58, there's a little peak in here. We still have a little bit of the original acetanilide. However, this is the brominated product. So there are only 2 peaks in here. The baseline is clean, a little guy in here, and then the big peak in here. And then it's going to end at 3 minutes over here. So we're almost there. And then at 3 minutes, it's done. Done.